Part 2. The finance functions of calculator. Time value of money and bond. Hi everyone. After watching video part 1, we are now ready to get into the finance functions of the calculator. In this video, we are going to explore the topic of time value of money and bond valuation using the finance key functions of the calculator. These are the learning objectives. After watching the video, you will understand the following. Effective and nominal rate conversion. In this section, I will bring you through the concept of effective annual rate, EAR, and nominal interest rate, and how we are going to convert the nominal into effective annual rate or vice versa using the calculator functions. Before we develop further, the difference between effective annual rate EAR and nominal interest rate needs to be established. Interest rate represents the price of using money. However, there are different types of interest rate in the market, and usually interest rates are quoted in terms of nominal interest rate. One major difference between EAR and nominal interest rate is that nominal interest rate are quoted without consideration of the effect of compounding, that is, interest earned on interest. After considering the effect of compounding, the true interest rate is what we call as EAR. So what is compounding effect? In simple words, it is interest earned on interest. Interest earned on an investment is then reinvested into the cash flow to earn more interest, resulting in an exponential growth of money, as we can see in this graph. The effect of compounding effect depends on the compounding frequency, which relates to how many times interest is calculated and reinvested within a period of time. The higher the compounding frequency, the more frequent interest is calculated, and the stronger the compounding effect, which will result in a steeper exponential growth of money. Going back to the previous slide, as we mentioned before, the main difference between EAR and nominal interest rate is that the nominal interest rate does not consider compounding effect, whereas EAR does. Therefore, EAR represents the true interest rate that one earns or pays at the end of 1 year. It can be used to compare the interest rates between loans with different compounding periods where the nominal interest rates are quoted for. On the other hand, interest that is calculated more than once a year, quoted in yearly basis, is nominal interest rate. However, it does not take into consideration of compounding effect. For example, 12% per annum compounded monthly is equivalent to 1% per month effective. So every month, interest is calculated based on 1% interest rate per month, and it is then reinvested into the cash flow and earned interest on interest. So over 12 months, you are actually earning more than the nominal rate being quoted as 12%. This 12% is nominal interest rate, and EAR of this nominal interest rate gives you the answer about the true interest earned over the 1 year period. Let's look into an intuitive example. Suppose $100 invested today at a rate of 10% per annum, compounding semi-annually. So since 10% nominal rate does not consider compounding effect, we can evenly break it into two semi-annual periods for 1 year, with each semi-annual period earning 5% interest. By 6 months' time, $100 principal will grow to $105, and the interest earned over these 6 months is $5. And this is added to the principal, becoming a total of $105. And by another 6 months time later, $105 will grow to $110.25. So effectively, over the 1 year period, out of $100 principal, I am earning an interest of $10.25, which gives me a rate of 10.25. And this is EAR. So effectively, I'm earning 10.25% per year, even though the quoted nominal interest rate is 10% per year. This is because the nominal interest rate does not consider the compounding effect. So in general, we have this formula for EAR, where M represents the compounding frequency, as in how many times interest is compounded within a year. I represents nominal interest rates. Let's try to apply the concept into this example. So what is the effective annual rate of interest of 10% nominally if interest is compounded monthly? So compounding frequency M is 12, because when this interest rate is compounded monthly, it means that the interest is calculated monthly and is added back into the principal to earn more interest. And there are 12 months in a year. And I, nominal interest rate is 10%. By applying the formula, I have an EAR of 10.471%. So effectively, I'm earning 10.471% over 1 year of my investment at a nominal rate of interest quoted at 10% per annum. Now, in our financial calculator, these are the keys that we are going to convert nominal rates into EAR or vice versa. In your calculator, it is located right here. The keys for interest rate conversion are the orange secondary function. The orange function under IYR records the nominal interest rate, whereas the orange function under PV is the effective annual rate. First of all, clear all memory, shift down C. Then enter the correct payments per year. The nominal interest rate in this example is 10% compounded monthly. Therefore, we need to set our calculator into 12 payments per year mode. By clearing all memory, you should be able to confirm which payment per year mode the calculator is set. So it says 12 payments per year. If the calculator does not show 12 payments per year, you need to set the calculator into the correct payments per year mode. So in this case, it is 12 payments per year. So how do we switch that? 12, and you will see the payments per year as an orange secondary function under PMT. So to get that, shifts down and then PMT. and then clear all again to check whether you are in the right mode. Next, enter the nominal rate, which is 10%. To get to the nominal rate, you need Shift down and that button. To solve for effective annual rate, press Shift down and PV. And your final answer is the same as what we have manually calculated before. So this is how we convert the nominal interest rate into effective annual rate and vice versa. Now, you can pause the video and try the following questions. Okay, in the next section, I will bring you through time value of money, particularly how to compute present value and future value, or solve for interest rates and the number of periods using our calculator. Let's start with the concept of present and future value. I will use a timeline to help illustrating the concept clearer. One important thing that you need to understand is $1 today does not equal to $1 tomorrow. And this is the fundamental knowledge of time value of money. So present value, PV, represents the current worth of a future sum of money or a series of cash flow at a specific rate and return. Whereas future value is the value of a sum of money or a stream of cash flow in the future based on an assumed rate of growth over the time. First of all, let's consider just a single lump sum of money that occur on the timeline. We have our formula to compute PV and FV for annual compounding. For compounding frequency more than once a year, we have our formula for PV and FV here. Note that the difference between the left column and the right column is that for M compounding frequency, we need to adjust for the interest rate by dividing the nominal interest rate I by M, making it to become the interest effective for that particular period. And we also need to adjust for the number of years by multiplying M, making it to become the number of periods. For example, if it is a quarterly compounding rate, M is equal to 4 because we have 4 quarters in a year. Therefore, the yearly nominal interest rate per annum is divided by 4 to become the interest rate effective per quarter. And the number of years is multiplied by 4 so that we have the number of quarters periods. In our calculator, we are going to use these buttons. N represents the number of periods. It can be years, semi-annuals, quarters, months, days, etc. depending on the compounding frequency. IYR represents interest rate. PV stands for present value. FV stands for future values. And they are located right at the top row of our calculator. Note that the payment per year function, which is the secondary function below PMT button. This allows us to change for different compounding frequency. The default status for calculator is 12 payments per year mode. You can check that when you clear all the memories of the calculator. We have already seen that in the example before when we convert the nominal into effective rate. So for annual compounding, we use 1 payment per year mode. For quarterly compounding, we use 4 payments per year mode. Let's set the calculator into 1 payment per year mode. So press 1, then payment per year. To reach that, you need shifts down and then PMT. And check the payment per year mode by clearing all the memory again. Example 2. Find the present value of $300 in year 5 at an interest rate of 10%. So first of all, clear all the memories and make sure that it is in the right payment per year mode. Then input figures as tabulated. So we have $300, which is our future value. In year 5, so 5N, and an interest rate of 10%. So in this case, we need to enter the full interest rate in percentage form. To solve for PV, press PV, and your final answer is 186.28. Note that you will see a negative sign in front of the answer. Ignore the negative, and your final answer is a positive number 186.28. The negative is shown here because that's the language of the calculator, indicating that the PV and FV is in the opposite side of the formula. If you enter FV as a negative, you will get a positive PV. So this is something to be mindful of. Dollar value on the opposite sides of equation cannot be assigned the same sign when using the calculator. So by convention, we usually assign a negative sign to the PV and positive sign to FV. This is particularly important when you are asked to solve for other variables than FV and PV, such as interest rates and N. Besides the signs of variables, when interest rate is not annually compounded, we mentioned before that we need to adjust the yearly nominal interest rate into the interest rate per period and the number of years into the number of periods. So for manual calculation based on the formula, this is how we are going to adjust. Firstly, identify the compounding frequency M. For example, if it is a semi-annual compounding, M equals to 2 because we have 2 semi-annuals in a year. If it is a quarterly compounding, M equals 4 because we have 4 quarters in a year, so on and so forth. After identifying M, formula will then be adjusted accordingly. So how are we going to do this in our calculator? So there are basically 2 ways. I will demonstrate you with two different approaches using an example. Example 3. Find the present value of $300 in year 5 at 10% interest rate, but in this time it is quarterly compounded. So we have two approaches to solve for PV in this situation. Firstly, we can set our calculator into the right, correct, and payment per year mode. So in this case, it is 4 payment per year mode. Alternatively, we can still stick with 1 payment per year mode. So either way, first of all, clear all memories and check the payment per year mode. So in our first approach, we need to set the calculator into 4 payments per year mode. So press 4, shifts down and PMT, clear all to check that again, and then input the figures as tabulated. So 300 FV, N represents the number of periods, so we have 5 years, 4 quarters in a period. So 5 times 4 equal, and that is our N. IYR is the quoted nominal rate, which is 10% here. So 10 IYR. To solve for PV, press PV button, and the final answer is $183.08. In the second approach, we use 1 payment per year mode. You may feel it is incorrect because interest rate is compounded quarterly, and why are we still using 1 payment per year mode? It is still feasible, as we are now treating 1 quarter as if it is a 1-year period. So clear all again, and 1 payment per year mode. Clear all to check that. So 300 FV. N is our number of periods, so 5 times 4, we have 20 quarters over 5 years. And now interest rate here, we need to adjust the interest rate, as in it is treated as in 1 year. So we need a quarterly interest rate, which is 10 divided by 4. And that is IYR. So, in other words, it is 2.5% per quarter effective. To solve for PV, press PV button, and the final answer is the same. What are we trying to do here is that we are treating the quarters as if it is in the number of years. Therefore, treating the number of quarters as number of years and quarterly interest rate as yearly interest rate in order to find the PV. So, by adjusting N and IYR, this is more in line with our formula shown before. Whereas in the 4 payment per year mode, only the number of periods needs to be adjusted, not the IYR. So for this reason, I would prefer 1 payment per year mode because this is more in line with the formula. When we have compounding frequency more than once per year, we adjust both interest rate and the number of periods. Now, you can pause the video and try the following questions. Okay, so we have learned how to compute present value and future value of a single sum of money. Now let's move on to a series of equal cash flows happens at equal interval on the timeline. So this type of cash flow is called annuity. Basically, we have two different types of annuity. We have ordinary annuity and annuity due. With ordinary annuity, payments are made at the end of the period. One example of ordinary annuity in the real life is the interest payment made from the bank to a depositors. With annuity due, payments are made at the beginning of the period. For example, the rental payment, which is usually made at the beginning of the period. And the key strokes that we are going to use for this type of cash flows are N, representing the number of periods. So again, it can be years, semi-annuals, quarters, months, days, etc., depending on the compounding frequency. IYR, interest rate. PV represents present value. FV represents future value. And we have also PMT, representing payment per period. And these buttons allows you to toggle between beginning and end mode. So ordinary annuity has to be operated using end mode. Annuity due has to be operated using beginning mode. With the different types of annuities, we need to make sure that the calculator is set correctly. So again, if it is an annuity due, payments are made at the beginning of the period. So we need to set the calculator into the beginning mode, BEG mode. So it is located as a secondary function under MAR button right here. By default, the calculator is in the end mode. That is for ordinary annuity. When you have an annuity due, you need to change or you need to toggle from the end mode into BEG mode. To get that, press Shift down and MAR, and you will see the BEG annunciator appear on screen. And for ordinary annuity again, press the same button to make the BEG disappear. So something to be mindful of. First of all, please make sure that your calculator is set in the correct payment per year mode or the mode that you want to operate on. As I mentioned before, one payment per year mode is always preferred because it is more in line with the formula. Secondly, after annuity due calculation, please make sure that you set your calculator back to the end mode before the next calculation. For example, if I'm doing annuity due question, so I need to set it to BEG mode. Once the question is done, you need to make sure that you toggle it back to the default status, which is the end mode. Because if you just clear all the memory, it will not clear the BEG mode in the calculator. Let's try another example. Find the PV of a series of $300 payable semi-annually for 10 years at an interest rate of 10% per annum compounded semi-annually. And it is told that the first payment is made at the end of the first year. So first of all, let's note down some facts. This is an ordinary annuity because the first payment is made at the end of year 1. And it says semi-annual payments are made and the interest is compounded semi-annually. So we can identify the compounding frequency M that is equals to 2. So in this case, by referring to the formula, we know that we need to adjust the interest rate by dividing the nominal interest rate by 2 and the number of periods, multiplying n by 2. In our calculator, as we mentioned before, we can solve this issue using two approaches. One approach is to use 2 payment per year mode, or alternatively, we could use 1 payment per year mode. Since 1 payment per year mode is always preferred because of the fact that the adjustment to the compounding frequency is more in line with the formula, I will demonstrate using the 1 payment per year mode. First of all, clear all the memory and check for the payment per year mode that you wish the calculator to operate on. Then input the figures accordingly. So the semi-annual payment is 300, so PMT, and we have 10 years and 2 semi-annual in a year, so 10 times 2, that is our number of period. Interest rate, 10% nominal interest rate, so we need to make it to the semi-annual interest rate effective, so 10 divided by 2, this is our interest rate. To solve for PV, press PV, and your final answer is 3738.66. Again, ignore the negative sign. It is because PMT is entered as a positive value. And because PV is at the opposite side of PMT, it is returned to be a negative sign. Now, please pause the video and try the following questions by yourself. Okay, mortgage loan or housing loan is one of the examples of annuity, and we are now ready to take a step further to look into how we can apply time value of money into practice. In this example, consider that you need to finance the purchase of a house, and the purchase price is 550,000, and you will require 100% financing. And the loan term is 30 years, and the terms of the contract require monthly end of period payments, including interest and principal. And the current variable rate offered by your bank is 6% per annum. So before we go into further, with the information given, we are able to determine the variables. The purchase price was 550,000. And by requiring 100% financing, you will be obtaining the full 550,000 from your bank at the beginning to settle the purchase of house. That is the present value. And this is a 30 years loan with monthly payment. Therefore, N has to be adjusted, so we have 360 months. Nominal interest rate quoted by the bank is 6% per annum, and this is equivalent to 0.5% per month effective. So the missing variable is the payment, which is the question for part A. Remember that we have two options to solve the time value of money problems when compounding frequency is more than once per year. I will demonstrate you the 1 payment per year mode using the calculator, and please refer to the alternative approach, which is also shown in the table here. So first of all, clear all the memory, shift down and C, and check for the correct payment per year mode that you want the calculator to operate on. Then input the variables accordingly. So PV 550,000. We need to input this number as a negative figure. So we use a change of sign button. Remember, variable opposite to each other cannot be assigned the same sign. So to get a positive PMT later on, PV now is set to be negative. So PV. Next, since this is monthly payment, so the compounding frequency is monthly. So my calculator is in one payment per year mode. So we need to adjust both N and IYR. So N is 30 times 12 N. So we have 30 years with 12 months in a year. And interest rate is 6% per year divided by 12. 6 divided by 12. That is our interest rate. To solve for monthly payment, press PMT, and the final answer is 3297.53. This is the payment that you need to pay monthly for 30 years long for your mortgage loan. So using 12 payments per year mode, IYR does not need to be adjusted, which is the full nominal interest rate of 6% per year. Part B. If you are selling the house 5 years after the mortgage start, how much do you still owe the bank? So this question is asking for mortgage balance. When you wish to close off your loan earlier than the offered term, your bank would ask you to pay a lump sum which represents the remaining outstanding payments. So you need to compute the present value at time 5. That represents the present value of all the future outstanding monthly payments. So to execute that, again, I'm demonstrating one payment per year mode. So my payment is 3297.53. Again, I make this into a negative figure. So this should be a plus minus sign. That is my PMT. So same thing here. To return a positive PV, so PMT needs to be negative. And now, at time 5, I'm still left with 25 years term of the loan. So my outstanding months of payment is 25 times 12. So 25 times 12, that is my number of periods, number of months. Interest rate is still the same, so 6 divided by 12. And to solve for PV, this is the PV at time 5, so we press PV. So the final answer is 511,799.29. So this is the PV at time 5, representing the present value of all future outstanding balance. And this is the lump sum that you need to pay your bank to close off the loan if you want to sell the house. And again, for 12 payments per year mode, please follow the left column. Part C. Part C is asking that 5 years later, after the mortgage start, you are now earning a bit more in your job, so you decide to pay an extra $500 every month into your mortgage. What impact would this have on the remaining terms of your mortgage? So in this case, payment has increased from 3297.53 to 3797.53, which is $500 more. And now we are asked to solve for n. So in one payment per year mode, again, my PMT now is $500 extra, so 3797.53. Make it as a negative. Remember to give a negative sign to this figure, and PMT. IYR interest rate is the same, 6 divided by 12. PV is the PV at time 5, which is 511,799.29. So in this time, PV has to be a positive because PV and PMT, the dollar values at opposite sides, cannot be assigned as the same sign. So we have already given a negative sign to PMT, so PV has to be entered as a positive value. To solve for the number of period, press N, and your final answer is 224.64 months. So by dividing it by 12, you get 18.72 years. So instead of 25 years remaining, by paying $500 extra per month, so you are expected to fully pay the loan by approximately 19 years, in which shorten the term of the loan by approximately 6 years. Bond valuation. So in this section, I'm going to demonstrate how to solve the coupon paying bond problems using our calculator. In our calculator, we have the bond function keys, so which are located at the top 2 rows, the secondary blue functions. Alternatively, we can also solve the bond problems using time value of money keys, which we have already seen in the previous sections. And this is actually the preferred method. Nevertheless, I will still demonstrate the computation using both approaches. First method, using bond functions. Before we go through this example, I would like to briefly bring you through the bond function keys in our calculator. So in the first row, blue function, we have the accrued interest, yield to maturity, price of the bond, coupon rate, and the call value, which is also the face value. In the second row, the blue functions, we have the format for the date, and this is the key to set the format of the dates, whether you want the calculator to read the date input as date, month, year, or month, date, year. The default setting of the calculator for the date format is month, date, year. Then semi/annual is the coupon frequency, so which refers to whether it is a semi-annual coupon paying bond or annual coupon paying bond. Bond with annual coupon payment is the default mode. Set date is the starting date or settlement date when the bond is purchased. Met date is the maturity date of the bond. Now let's look at this example. What price should you pay on April 28, 2010 for a 6.75% US Treasury bond maturing on June 4th, 2020, if you want a yield of 4.75% and pays a semi-annual coupons, assuming the face value is $100. So first of all, clear all memory, shift down and C, or clear the bond memory. So to clear the bond memory, shifts up, C and 7. Next, set the coupon frequency. So this is a semi-annual coupon paying bond. So we need to make sure that the calculator is set into the semi mode. So to get that, shifts up and CST. So you will see the semi annunciator appears. Next, set the starting date. By using the default setting, which is month, date, and year, so our settlement date is on April of 28, 2010. So we need to input the month April dot 28, 2010. And that is to set the date. Next, to set the maturity date, which is on June the 4th, 2020. So 6.04 2020 shifts up met date. Set the coupon rate. So this coupon paying bond has a coupon rate of 6.75%. So 6.75% coupon rate shift up PMT. Call value or face value is 100. So 100 shifts up call value. And this bond has a yield of 4.75. 4.75 shifts up yield to maturity. To solve for the bond price, shifts up PV. This is the gross price. And we need to add if there is any accrued interest into the bond price to become the total price for the bond. So we need to plus any accrued interest. So shifts up accrued interest. And the screen now shows the accrued interest of 2.69 equal the total bond price of $118.55. Sorry, 58 cents. Second method, using time value of money keys. When the problems do not include the exact dates, TVM keys is a preferred method. So the cash flow of a coupon paying bond includes the regular payment of coupons for the term of the bond, and we also have a face value at the end of the maturity. So this is actually a combination of an ordinary annuity of coupon payments for the term of the bond and a single sum of the face value at the end of the maturity. So by referring to the formula, the price of the bond is equal to the PV of all coupon payments. So this is an ordinary annuity plus the present value of the face value payable at the end of the maturity. So this is just taking the present value of a single lump sum. So in this case, it is easier to use the time value of money keys. So example, a 10-year treasury bond pays 6% per annum coupons semi-annually and has a face value of $100,000. The prevailing market rate of interest is 5%. What is the fair price of the bond? So the first variables needed here is the coupon payment in dollar value. And we know that we have a coupon rate per annum of 6%. So 6% of the face value, then divided by 2 because this is payable semi-annually per annum. Then the second variable is the yield, which is the market rate of interest 5%. And because the cash flow is payable semi-annually, with a compounding frequency of 2, we need to adjust the interest rate by dividing it with 2. So it becomes 2.5% per semi-annual. Third variable, which is the number of periods. And so it is 10 years times 2 because we have 2 semi-annuals in a year. So it becomes 20 semi-annuals period. And we have the last variable here, which is the face value, which is just $100,000. So in our calculator, I'm going to show you the one payment per year mode, even though you can also use the 2 payment per year mode in your calculator. So first of all, clear all memory, shifts down C, or clear your time value of money memory, so shifts up C1. Make sure that you are in the correct payment per year mode that you want the calculator to operate. So in this case, I'm demonstrating you one payment per year mode. So after clearing the memory, set the payments per year, which is already in one payment per year mode. Then set the face value, 100,000 face value. Coupon payment, as we mentioned before, it is equals to the 6% annual coupon rate. We need to use this to multiply the face value and then divide it by 2. So your face value is 100,000 now, multiply by 6%, so 6% divided by 2. So 3,000 is our semi-annual coupon payment. So that is PMT. Total payments. So we have 10 years, 2 semi-annuals per year. So we have 20 semi-annuals, 20 payments of coupons. Interest rate, 5% per annum divided by 2. That is your interest rate. To solve for the price of the bond, press PV, and this is your final answer, 107,794.58. Alternatively, you can use 2 payment per year mode, and everything is the same except for the market interest rate. And this has to be a full per year figure. Now, please pause the video and try the bond problems by yourself. Thanks for watching the part 2 video. So next up, I will bring you through the finance functions of cash flows, particularly how to enter a series of cash flows into the cash flow memory of the calculator to compute for net present value. So following that, I will also bring you through the statistical functions of the calculator, specifically entering a series of data into the calculator for statistical outputs.